Last chapter, common solids. Solids come in different sizes and shapes. While some solids are made up of flat surfaces, some are made up of curved surfaces. Many others are a combination of different surfaces. And just like plane figures, solids have distinct features. The flat surfaces of a solid are called its faces. They are in the form of plane figures. In the given figure, the total number of faces is 6. A top, a bottom, and 4 around the sides. The line segments where two faces meet are called edges. Here we have 12 edges. A vertex is a point where two or more straight lines meet. Here we have 8 vertices. This solid is made up of 6 faces, 12 edges and 8 vertices, and is called a cube. This solid too has 6 faces, 12 edges and 8 vertices, but it's called a cuboid. So whereas a cube has square faces, a cuboid has rectangular faces. This is a prism. It has 5 faces, a top and a bottom, which are triangular. The other 3 faces are rectangular. It has 9 edges and 6 vertices. More shapes, sphere, cone, and cylinder are curved figures. So they neither have straight edges nor any vertices. As for faces, a sphere has not a face. A cone has 1 circular face and a cylinder has 1 or 2 faces. If it is open on one end, it will have 1 face. But if it is closed, it will have 2 faces. A hollow cylinder does not have any face. Next, drawing solids. Now, we use certain rules while representing solids to allow us visualize them quite accurately. For example, each face is defined by the lines enclosing them. The edges that are visible from the angle of view are drawn with continuous lines, while the invisible edges are drawn in broken lines. For instance, the 3 edges of a pyramid that are not visible from this angle of view are indicated by the broken lines. Now let's view a cube from this angle. These faces are in direct view. These are the defining lines in our view. So the lines are continuous. Then the broken lines will represent the edges that are not visible. And so this is a representation of a cube solid on a flat paper. This is a cuboid with 6 rectangular faces. And this is the representation from our angle of view. This is a triangular prism. It has 2 identical faces parallel to each other. If you cut the solid parallel to these faces, you will see that the cross-section obtained will be exactly like the 2 identical faces. The name prism is used to refer to a solid with a uniform cross-section. This is a triangular prism because the cross-section is a triangle. The solid has 5 faces in total. Now here is a different prism. Here, the parallel faces are pentagons. The prism has 7 faces. This is a cylinder. A cylinder is a circular prism with a curved surface. This is a pyramid. Pyramids have a flat base. The area of cross-section of a pyramid reduces upwards, so a pyramid is not a prism. The base can take many shapes. The faces forming the sides, however, are all and always triangles. These triangles meet at one point. This figure is a solid cone. It has one flat surface and one curved surface. A cone is similar to a pyramid but has a circular base, so a cone is also not a prism. From the definition of a prism, it means that a cuboid is a rectangular prism and a cube is a square prism. Nets of solids. The net of a solid is a flat figure that can be folded to get the shape of the solid. The lines are the places where folds occur. Notice in a net, we have each shape sharing at least one of its sides with another face. So simply, a net is a view of the solid surface spread flat. In other words, it is a two-dimensional figure that can be folded to form the three-dimensional solid. So we can make a net for this cuboid. Notice that this net is not unique. This means that there can be different nets for the same cuboid. As long as a net can be folded into the required solid, we say it is a net of the given solid. The order of attachment of the sides in a net is important because in folding a net, no shape should be detached from its position. So can you identify the net of the solid? We see that only B can be folded into the solid. In order to draw the net of a solid, always note the number of sides it has and the shape of the faces first, and then proceed to visualize whether the net can be folded to form the given solid. For instance, this is a triangular prism. If we unfold it, we obtain this net, 3 rectangles and 2 triangles. The attachment of these shapes on the net is very important because their mere presence does not always mean it's the required net. Consider this net with the 3 rectangles and 2 triangles, but attached differently. If we fold it, one triangle does not take its place, so the triangle is in the wrong place on the net. Take a look at these nets and try and visualize how they are folded to form the solids. Lastly, we shall look at the surface area and volume of solids, and in particular we shall look at the cylinder and a cone. We start with surface area of a cylinder. So here is a cylinder of radius r and height h. If we open up this cylinder, we shall have the top and bottom circles, and the curved surface will unwrap into a rectangle of width h. What will be the length? Since the curved surface does not overlap, it is easy to see that the width of the rectangle is equal to the circumference of the circles. We know that circumference is equal to 2 pi r, and so the width of our rectangle is 2 pi r. It follows that the area of the curved surface is given by area is equal to 2 pi r times h. The area of the circle is of course given by pi r squared. It is important to know whether the cylinder is closed or open on one end. If it is open, then there is only one circle. If however the cylinder is closed, we will multiply this by 2. So total surface area is equal to 2 pi r squared times h, the surface area of the curved surface, plus pi r squared, the surface area of one circle, plus pi r squared, the surface area of the other circle. That gives us 2 pi r h plus 2 pi r squared. We can factorize 2 pi r and we shall have 2 pi r into h plus r. This is the formula for finding the total surface area of a closed cylinder. Now we look at a cone. The solid obtained by revolving a right-angled triangle about one of its sides apart from the hypotenuse is called a cone. In this cone, AB is the perpendicular height h, BC is the radius of the base of the cone, and AC is the slant height L of the cone. When the curved surface of a cone is opened up, it appears like a sector of a circle. The base is of course a circle. Notice now that the slant height L of the cone is actually the radius of the original circle before it was folded into a cone. The curved length of the arc of the circle is equal to the circumference of the base of the cone, 2 pi r. Remember, r is the radius of the base of the cone. Very so often, many students think that the angle theta of the sector of the circle is the same angle at the vertex of the cone, but it is not. If you carefully look at the opening of the cone, you will appreciate that the angle formed by the sector is larger than that of the cone. The surface area of the curved surface of a cone is given by pi rl, and of course that of the circle is given by pi r squared. So total surface area is pi rl plus pi r squared. If you factorize pi r, you'll have pi r into L plus r. It is important to always know whether the cone in question is opened or closed in order to include or exclude the area of the circular base. Notice that when we open a cone, it is no longer possible to see the perpendicular height h. Next is volume. We know the volume of a cylinder is given by volume is equal to pi r squared times h. For solids with uniform cross-section that we call prisms, volume is given by cross-sectional area times height or length. A cylinder is a circular prism. The cross-section is a circle whose area is pi r squared. So looking at the formula pi r squared h, the part pi r squared is the cross-sectional area. Now this is a cone. A cone has no cross-section. The volume of a cone is given by a third base area times the perpendicular height. The base of a cone is a circle, so base area will be given by pi r squared. So the formula above can be rewritten as volume is equal to a third pi r squared times h. If you look at this formula, you will see a relationship with that of the cylinder. If you remove a third, what remains is the volume of the cylinder. In truth, if you have a cone with the same radius and height as a cylinder, the volume of the cone will be a third of the cylinder. And so if you fill the cone with water and transfer it into the cylinder, the water will fill a third of the cylinder.
One of the wonderful things about mathematics, I think, is that people are impressed. It's often seen as a very hard subject, and so if you've done math, it's often treated as an entrance requirement, as a credential to do lots of other things. And so one idea is that for example, some MBA programs, the only thing they require going into it is a good, solid math understanding. They can teach you all the business, they just can't teach you the math fast enough. And so I think that math, aside from obvious careers that require math, if you're going to go work in a department that does operations research or something like that, they'll want people with specific skills in mathematics. But math is often seen as a filter or as a screen for many, many other disciplines. And so I guess what I'm trying to say is you can think broad, because math actually is a solid preparation. It's a good credential to go into lots of different fields that people often don't consider at the beginning.